So in the second part, we are going to compute the expected value of the absolute value of z, where z is a standard normal random variable, which has the expected value equal to 0 and standard deviation or variance equal to 1. So what is the expected value of the absolute value of z? Now, how do we solve such a expected value? Now, remember, we have an integral of function itself multiplied with the probability density function of the input variable. So the PDF of the standard normal random variable is phi(x), and the function inside the expected value is an absolute value function. Now, my friends, you know that the absolute value function, it's not a differentiable function. So in this form, we cannot calculate that integral, right? Because the absolute value function, it's not a differentiable function, as you can see here. I mean, I'm going to explain this to you easily. You know, we have x and g of x here, g of x here. The absolute value function is a function like that. And that function, the absolute value function, is not differentiable at this point. Why? Because the right limit of the first derivative and the left limit of the first derivative are different. Even though the function is continuous at that point, the function at that point is not differentiable. So therefore, we cannot calculate that integral. However, you know, the absolute value function is defined in this form. So if the input value x is greater than or equal to 0, in that case, the absolute value of a value is itself. However, if the value inside the absolute value is negative, if it is negative, in that case, we multiply that negative value with -1 to calculate the absolute value, right? So actually, the absolute value is like this. In that case, I can calculate this integral from -infinity to infinity. I can calculate this integral by partializing it into two sections, where in the first section, the x value is negative from -infinity to 0. And in the second part, it is from 0 to infinity positive. And when x is positive, I know that the absolute value is equal to x itself. And when x is negative, I know that the absolute value of x is equal to negative of x. So therefore, I need to calculate these two integrals. And now when you check these two integrals, these integrands are differentiable. So maybe we can calculate these integrals. Now, if you remember from the last week's lecture, I have shown you, okay, I have shown, actually, showed you, I have shown that the probability density function of a standard normal random variable is this. And when you calculate the first derivative of the probability density function, you get -x times the PDF itself. So the first derivative of the PDF is equal to -x times the PDF itself. So as you can see, we have -x to PDF itself here. So that integrand is the same as the first derivative of x. And here we have x times phi(x), not negative, but x times phi(x). So we can write, instead of that integrand, we can write the negative of the PDF, the first derivative of the PDF. Okay, so now these integrands are much easily integrated, right? So what is the integral of the first derivative of phi(x)? It is phi(x). And here again, because we have this minus sign outside the integral, the first derivative, the integral of the first derivative is again equal to phi of x. So all we need to do is to calculate the result of the first integral. We are going to plug in the upper bound 0 and the lower bound -infinity to phi(x). And in the second integral, we are going to plug in the upper bound infinity and the lower bound 0 to phi(x) again and take the difference. Then we are going to take the difference of these differences as well. So let's calculate the first part. Now, if you remember, my friends, so the distant education's good side is this: you do not lose any time when you want to erase the board, okay? So erasing board takes some time. in regular education, but here in in Paint, it is very easy. So this is the PDF. So this is the PDF Phi-x, okay, Phi-x here. And that PDF has the expected value of equal to 0. And as a result of the first integral, I need to compute Phi-x at 0 and minus infinity and take the difference, okay? So what is the value at minus infinity? The value at minus infinity at 0, as you can see. So the result is something minus 0. And what is the value at 0? So the value at 0 is going to be equal to 1 over square root of 2 pi. Okay? Why? Because, you know, my function is equal to 1 over square root of 2 pi e to the power minus x squared over 2. And if x is equal to 0, e to the power 0 is 1. So the result is 1 over square root of 2 pi minus 0. And for the second integral, the result is 0 minus 1 over square root of 2 pi. And when you subtract minus 1 over square root of 2 pi from 1 over square root of 2 pi, you get 2 over square root of 2 pi. And that is approximately equal to 0.7979. Okay? So the expected value of the absolute value of z is equal to 0.7979 approximately. So you see, my friends, actually, this is just a theoretical example. Maybe it may feel a little hard than the questions, ordinary questions that we are solving. However, if you understand what we are doing here, actually you are going to have a better idea about the normal distribution and how it behaves. Okay? So normal distribution or normal random variable is a quite interesting random variable. And as I have told you, the scientists have invented that random variable maybe 250 years ago. Okay? But I mean, at this point, we are experiencing very hard times to teach that random variable to engineering students who live in the 21st century. Okay? I mean, you are much more intelligent than the people lived in that area. Okay? So because of that reason, I think you are supposed to understand these things much more easily, but I think this is all related to the interest of the students. Okay, if you are interested, then you learn. Okay, so after solving this, we are going to see how we can calculate the variance of a function of a continuous random variable. Now this time, suppose x is a continuous random variable along with its probability density function f of x, and g is a real valued function which transforms our random variable into another value. And the variance of g of x is what? Again, just like the definition we have in the discrete case, it is the expected value of the square of the function of a random variable minus the square of the expected value of a function of a random variable. And because random variable x is continuous, we are going to calculate that integral. We are going to calculate that integral as g square x fx. For the first expected value, we calculate the integral of g square x fx from minus infinity to infinity. And for the second part, we simply calculate the square of the expected value of the function of a random variable. Now, we can learn about it by practicing it, obviously. So let's just say x is a continuous standard uniform random variable. Okay, x is a continuous standard uniform random variable. And we would like to calculate the variance of x to the power n. So y is a function of random variable x, which is calculated as x to the power n. We would like to calculate the variance of y. Y is a function of that random variable, which is again random. And n is a positive integer. We are supposed to calculate the variance of x to the power n. Okay? So the question is basically asking us this: what is the variance of y? And since I know the variance, the y is defined as x to the power n, I am supposed to calculate the variance of the x to the power n. which is going to be equal to expected value of the square of the function of a random variable, okay, minus the square of the expectation of the function of a random variable. Okay, so this is the thing that I am supposed to calculate, which is equal to the expected value of x to the power 2n minus the expected value of x to the power n to the power 2. Okay, now you know the expected value of x to the power n was calculated as 1 over n plus 1 in one of the previous questions that we have solved today in the previous hour. So what do you think the expected value of x to the power 2n will be? It is going to be equal to 1 over 2n plus 1, right? Yeah, that's easy. I mean, we are not supposed to calculate the integral in any way, but if you are really interested calculating in that integral, you are supposed to be calculate the integral of x to the power 2n multiplied with the PDF of the standard normal random variable, which is basically 1. Between 0 and 1, you are going to calculate that integral, and that is going to result with 1 over 2n plus 1 here. Okay? And the result, my friends, in that case, so we know that expected value of x to the power 2n is 1 over 2n plus 1, and the expected value of x to the power n is 1 over n plus 1, and we square it, and after squaring it, you are going to have some complicated algebra here, and in the end of the algebra, unfortunately, you are not going to get a very friendly closed form formula. It is not going to be very friendly, but it is going to read as n squared over 2n plus 1 times n plus 1 to the power 2. Okay, so we have computed the variance of a function of a random variable in an easy manner. Now we are going to come to the most important part of this lecture, of this chapter, not lecture, but this chapter. So the most important part of this lecture is the last chapter, okay? However, for this chapter, the most important section is this section, the last section, okay? Now, for years and years, I have always asked questions related to that section in private universities, okay? So I am giving this course maybe how many times, for about how many times? Maybe this is going to be the 15th time, okay? In my 6 years of experience as an academician, maybe I have given this course more than 10 times, okay? I have always asked a question related to this section, okay? Unfortunately, none of the students can give a perfect answer. I mean, I got good answers when I was a teaching assistant at Boğaziçi University, but in private universities, I think I haven't got any fully correct answer for a question related to this chapter. Actually, this chapter is not a very hard chapter, okay? However, I really do not understand. Maybe the students do not understand the concept here, okay? So remember, for discrete random variables, when we were studying the discrete random variables, we have first learned how to calculate the expected value of a function of a discrete random variable, then learned how to calculate the variance of a function of a discrete random variable, and then we have learned how to determine the probability mass function of a discrete random variable. And in the previous hour, we have solved this simple example, and in this simple example, you have seen that for discrete random variables, the probability mass function of a random variable can easily be determined by a straightforward procedure, okay? So in this example, it is very pretty well comprehensible. However, this time we are going to do the same for continuous random variables. So we are going to determine the distribution of a function of a continuous random variable, and obviously, it is going to change, right? So the distribution of a function of a continuous random variable is going to be different than the distribution of the input variable. So the response is going to have a different distribution than the input. And therefore, I am just going to use a methodology where we are going to determine the probability density function of the function of a continuous random variable. Okay. Now, suppose now x is a random variable. It is a continuous random variable, and it has the probability density function fx. So this subscript x indicates that this PDF function belongs to random variable x. And we further suppose that y, random variable y, is equal to g of x, which is a real valued transformation or real valued function of the input random variable x. So y is the response variable, the output, and x is the input variable. Okay. And then my objective is this. I want to determine the distribution of y. I want to determine the distribution of y. And how do I determine the distribution of y? By determining its cumulative distribution function, fy of y. Why I would like to determine the cumulative distribution function? Because if you determine the cumulative distribution function of y, then by taking its first derivative of the CDF, by taking the first derivative of CDF, you can also determine the probability density function of y. Of course, I'm here assuming that y is also a continuous random variable after this transformation. Okay, so in these examples, in the following examples, we are going to talk about transformations G such that they transform a continuous random variable again into another continuous random variable. Okay, so they do not discretize the input variable. They transform the input variable again with a continuous to a continuous random variable. So if I identify the cumulative distribution function of y, then by taking the first derivative of the cumulative distribution function, I can also determine the PDF of y, which is my ultimate objective. So this is my ultimate objective. I would like to determine the probability density function of the response variable y. So how do I do that? How do I do that? So first of all, I need to determine the cumulative distribution function of the input variable. So I have the PDF of the input variable, and I need to determine the cumulative distribution function of the input variable. So this is necessary. Okay. And I also need to determine the values that the y can take. So I know that x is a continuous random variable which can take a set of values over the real line. And with that set, and by the definition of function g, I need to determine the possible values that y can take. Okay, which values y can take. So I have determined the possible values that y can take. I have computed the cumulative distribution function of the input variable, fx. Now here's a thing here. Here's a theory. It says if the function g, if the transformation that converts the input random variable to the output is a strictly monotonic and differentiable function, then the procedure is very easy and straightforward, which we are going to practice today. However, if g here, the function g, does not satisfy these properties, any of these properties, then there is not a specified procedure. Finding the distribution of y may or may not be practical. So it may be possible or it may not be possible in that case. But we know that if g, the transformation g, is strictly monotonic. So what does that mean, strictly monotonic? If g is a function which always increases or which always decreases. Okay, if this g is a function like that, so strictly increasing like that or strictly decreasing like that, and it should be differentiable as well. So we should be able to calculate its first derivative. In that case, we can easily identify the distribution of y, the CDF of it and the PDF of it. There's a straightforward procedure. However, otherwise, in the other cases where we have a non-monotonic g or a non-differentiable g function, in that case, there is no specified procedure, but still it doesn't indicate that it is impossible. Okay, It may be possible or it may not be possible, it says. Okay? Now we are going to practice this. Okay? Please listen to me in these examples. I am going to apply the steps of the procedure here. Okay? So we have 4 steps here. Okay? The first step is to determine the values of y. The second step is to determine the CDF of x. Then we are going to apply a procedure where we are going to determine the CDF of y. Then we are going to take the first derivative of CDF of y, and we are going to determine the PDF of y. Okay? So the procedure is like that. The procedure is like that. First, I have the PDF of x, and from here, I am going to determine the CDF of x. And from here, okay, that's too long. From here, I'm going to determine the CDF of y. Okay, and from here, I am going to determine the PDF of y. Okay, so we are going to have a 4-step procedure here. But remember now, in the beginning, I need to determine the possible values of random variable y. Okay, the possible values of the random variable y. Okay, this is the first thing that I need to do. All right, so let's solve this first question. And the solutions are available in the presentation files. Can you follow me up, my friends? So let me ask you this. Can you follow me up? Are you ready to learn how we can determine the distribution of a function of a continuous random variable? So, okay. Let x be a continuous random variable with the following PDF. So x is a continuous random variable which can take possible values between 0 and 1. So it can take any real value between 0 and 1. It is a continuous random variable, therefore it takes any value within this interval, any real value, according to the probability density function 2x. Okay? Now, we define the random variable y as the square root of x. Okay? So y is a function of random variable x, and it's a real valued function. The question asks me this: what is the distribution of y? Or in other words, what is the probability density function of y? So we know the probability density function of x. What is the probability density function of y, it says? Okay? So let's start with the first step. So what is the first step here? The first step is the determination of the possible values of y. So you see, x can take, random variable x can take any real value within 0 and interval. So what are the possible values of y? So as you can see, if you take the square root of the values within the 0 and 1 interval, again, you will get values within 0 and 1 interval. So in this question, y can also take values within 0 and 1 values. Okay? So the possible values for y are real values between 0 and 1. So this is step 1. Step 2, we need to determine the CDF of x. Now the CDF of x is equal to 2t, right, as a function of t. If you write it as a function of t, I'm sorry, I am very sorry, we are calculating the CDF of x. The CDF of x means what? So let me write it here. The CDF of x means the probability of random variable x to take less than or equal values than lowercase x, which is the integral of the PDF, from minus infinity to x, right? So that is dt. The integral of the PDF from minus infinity to x. In this case, the PDF is 2t within 0, 1 interval, and elsewhere it is 0. So instead of integrating the PDF from minus infinity to x, we simply integrate it from 0 to x, assuming that x is within 0 and 1 interval, and it is going to be x squared as the result of the integral. So the CDF is simply equal to x squared for which values? For x values which are between 0 and 1. Okay? For these x values, the CDF is equal to x squared. Now I need to determine the CDF of y. So what is the probability? So instead of that, let me write it like this, x. So what is the probability of my output random variable y to be less than or equal to any x value? So whatever you would like to write here, it doesn't matter. You know, this is just an arbitrary value. If you prefer to use x or y, it doesn't matter. Okay? So the probability of y being less than or equal to an arbitrary x value is going to be the CDF, the cumulative distribution function of y. So let's determine the CDF of y, which is the probability of random variable y being less than or equal to y. So what is the definition of y, my friends? I have told you that y is defined as the square root of x. Y is determined as the square root of x. Therefore, I can replace that capital Y as square root of x being less than or equal to y. Okay? Now, the equation here, the inequality here is the same as, if you take the square of the both sides, the same as the fact that random variable x to take on values between 0 and y square, right? So that inequality and that inequality, they have the same solution space. So how do you keep x by itself only? By taking the square of the both sides. Square of the both sides. This means x is supposed to be less than or equal to y square. However, x also should be greater than or equal to 0 as well. Okay? So this inequality here and that inequality, these inequalities here, they have the same solution space where x remains in the middle and we have interval boundaries like that. Okay? So therefore, this probability is equal to the CDF of y at y. Okay? The CDF of y at y. Now, so as you see here, it has written instead of x. Okay, let me erase that x here. So instead of x here, it writes y. So let's just write here as well. We are going to write it here as well. So instead x, we write y. So for simplification purposes, maybe. So fy of y is equal to what? It is equal to the probability of random variable x to be less than or equal to y square, right? Because x is by nature greater than or equal to 0. So x is already greater than or equal to 0. Therefore, the CDF of y at y is equal to probability of x being less than or equal to y square. Okay? Which is equal to the CDF of x at y square. So that probability is equal to the CDF of x at y square. And the CDF of x is equal to x square, and the CDF of x at y square is equal to square of the y square, which is y to the power 4. Okay? Which indicates that the CDF of y is equal to y to the power 4 if y is between 0 and 1, and it is equal to 0 if y is less than 0, and it is equal to 1 if y is greater than 1.